Okay, so welcome to pattern analysis. We will continue our topic on clustering today and on the hyperparameters for clustering, choice of hyperparameters for clustering. But before we go into the details, let me bring something to your attention. So in our lecture on these little graphical models and these graph primitives, we talked about conditional independence. Yeah? And someone pointed out in one of the meetings with Shital that it's not so clear about a variable whether it's observed or it's unobserved. In the graphical form, an observed variable is indicated as a shaded node, and an unobserved variable is indicated as a not shaded node, like a normal node. But in the equations, it's not really clear from these equations. And this is actually a true point. If we look at the book by Bishop, so I'm here at essentially the same content here, page 375. Bishop is explicitly making a difference here if we look at A is conditionally independent of B given C, and A is not conditionally independent of B given none of the variables. So in that notation, if C is written there, it means like this is an actual observation. Yeah? And the empty set here indicates that we do not have an observation at this point. And in particular, I mean, it's a statement about A and B. So in particular, C is not observed in that case. I think it makes a lot of sense to make it the same in these slides. So just as an announcement, I will update the slides to match the notation that we have in the book by Bishop somewhere during this week. So this will affect these three slides on the conditional independence properties for these three graph primitives. Okay. Now back to our clustering topics. We, like last week and this week, we looked at a total of 3 clustering algorithms. K-means clustering, which was kind of a, you can say, hard clustering variant. No? Then we had the Gaussian mixture model clustering, which was the corresponding soft clustering version. So K-means and GMM clustering kind of form a pair, you can say. And for this week, we looked at a third variant, mean shift clustering, which operates in a different manner. So it performs a gradient ascent on a density that in some sense is obtained from a Parsons window estimator. So we're not estimating the full density with that Parsons window estimator, but we are estimating the gradient, and we walk towards the mode, so a high point, let's say, of that density. And this is the idea of the mean shift clustering method, and we can talk more about it today. And then the second question about this is, okay, what can we do about the choice of the hyperparameters for all of these 3 methods? Because the clustering task itself is a bit shakily defined. I mean, yes, we do have our objective functions, but it's not really clear like what could be a good criterion in such an unsupervised setting for the choice of hyperparameters. And this is like we can talk about all of this today. So I prepared a couple of questions, but if you want me like upfront to address something in particular, then we can do it. Or at any point later. We can quickly scan the questions here. So one thing that I want to discuss a bit more with you is this, the use of this Epanechnikov kernel. It's kind of a special kernel when it comes to the mean shift algorithm, because the mean shift algorithm becomes very simple when using this Epanechnikov kernel, and I wanted to discuss this a bit more. The second property that I wanted to discuss with you is like what consequences does it actually have to have a mode-seeking algorithm? No? When we think about different shapes of clusters that can be achieved, it's a bit of a more on the theoretical side, that question, because in practice, data oftentimes lumps together. So it's probably not super relevant in practice, but I think it's an interesting theoretical question how this objective criterion of the mean shift differs from the k-means and the Gaussian mixture models. Then I would like to talk a little bit about the hyperparameter selection scheme for k-means, so the so-called gap statistics, and understand this reference distribution a bit better. And yeah, eventually also just to close this, maybe have a closer look at the mean shift and Gaussian mixture model choice of hyperparameters. Okay, so this would be like my agenda for today, but we have enough time. We can anytime interrupt or deviate or so from that. Let's start with the Epanechnikov kernel. The Epanechnikov kernel, if we look at it in, I think, Wikipedia or so, then you will probably find a definition that is different from what is written on the slides. You know? Let's check. There's no Wikipedia nowadays anymore. There are these like quick results, but here, no. Do we have? Aha, yeah, so I think this is a very typical way of writing the Epanechnikov kernel. Sorry. So it's 1 minus, okay, we have some scaling factor in front, yeah, and then 1 minus input squared, yeah, and then if you plot this, it turns out, well, it's a parabola, no? Just like that. In our slides, it looks a little bit different, but only because our input is different. So we say we feed to this kernel profile, we feed a squared distance, a squared Euclidean distance. So it means instead of feeding a u, like a parameter u to that kernel, we effectively feed a u square already. And this means that we don't have the square in that equation. And we also don't have this prefactor, I think, constant in front. So this is what makes the difference, but otherwise it's really the same. Let's check the slides really quickly, just to have this. Yep. So this is the most laziest possible way of writing an Epernetchnikov kernel. So we say the input is already a squared distance. So this is a squared thing. And then it's just 1 minus x times some constant. But that constant also doesn't matter because this is essentially something that we can also fix with the size normalization of the kernel. Yeah, this is why the constant is missing. Okay. So this is the kernel profile if you're fine with the fact that there is already a square coming in. And now there's this curious behavior that states, a curious remark that states, with the Epernetchnikov kernel, the update of the mean shift iteration is just the mean of the samples within a d-dimensional sphere. And this is where the name mean shift comes from. Okay. So let's convince ourselves that this is in fact true. Here's our algorithm. We have in equation 11, we have this mean shift vector. Yeah? And then in equation 12, there is the update of the position in iteration t to a position in iteration t plus 1, like a new position. Yeah? And what happens? Okay, so what we can note here is this xt that cancels. So if we have the mean shift vector from iteration t in equation 11, we have minus xt. If we plug this into equation number 12, there we have plus xt, so the xt cancels. Yeah? It doesn't play any role in the calculation of the update position. We only have this gradient of our kernel profile here on the right-hand side that needs to be evaluated. This here, this expression. And now the question is, what happens with the Epernetchnikov kernel here? So what happens if, okay, what do we have? Okay, this is the derivation, okay. But let's check. So here in equation 3, we have our kernel profile. Yeah? So we have something like k of x equals 1 minus x if x is lower or equal than 1/2 or 0 otherwise. The difference between the and we are feeding squared distances to this, yeah, with x equals something like, or let me write u here just to be a bit clearer, yeah, with u being x 0 minus x squared. So we're feeding a squared distance to it, and then we have the 1 minus u here. What happens now? So this k prime is the derivative, no, of, no? So there's a derivative calculation. We have that k prime of s, but then there's also the differentiation of s towards x, so we need to apply the chain rule, no? But this is all included in the derivation of these gradient steps, no? So there was this like, okay, transform, 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 no? And then we ended up here. So this expression, the k prime of that input, is literally just the derivative of that kernel function without applying the chain rule. The chain rule is the reason why we are seeing here the xi and why we are seeing here the xt. Yeah. Okay. So these. So what happens in the chain rule is already taken care of. Therefore, if we just calculate k prime and calculate the derivative of k with respect to u, then it's just 1 that remains here. No? Okay, and then it's simple. No? So then you can say, okay, this is actually 1 times xi. Well, in case that we are within that range. No? If we are outside of that range, it just evaluates to 0. And divide, and then we get 1 per point in the kernel support range, or kernel support, yeah? And this is just the average, no? So then we have something like the sum over the xi in this neighborhood, yeah? Xi divided by, yeah, well, the number of points in that neighborhood, no? Effectively. So here we are counting like how many points are in that neighborhood. It's like we sum up a 1 for each of the points in that neighborhood. And here in the numerator, these points are just added up. And this is why it's just the average. So now you can write this as 1 divided by n times the sum over these xi of the points in the neighborhood. Yeah? Okay. And this is the reason why it's called the mean shift algorithm. It's a fairly simple operation. And this is what we have been seeing here in these animations. Yeah. This? This one. sorry, in the step between equation 8 and 9. So from 8 to 9? 9 and 10. Between 9 and 10. So between 9 and 10, hold on. So this part from equation 9 comes with plus to the right-hand side. Then the whole left and right-hand side are divided by this sum. Then we have this expression. And then with a minus, so there's only the x on the right-hand side, and this can be subtracted and then brought back to the left-hand side. Does that make sense?
The question is that the factor, multiplication factor and mean factor with xi are same. So can we cancel out?
Hold on, this xi?
Factor, yes, factor with this, the expression sigma 1 and I equal to 1 when? This factor.
Sorry, here? From I equals 1, the sum goes over the sum goes over all n points, all n observations, here on the left side, and also this sum here goes from 1 to n, right? Yeah. We can, if you tell me, we can keep talking about it. But yeah, like, is it okay, or shall we continue? Like, literally, we can continue. It's not a problem. No? But I guess I just didn't fully understand what the problem is. Yeah. So. So the sum includes the xi in any case. No? So this is one factor. This is one product here, and this is the other product. No? And we can think of this like this kernel profile. It gives us a weighting term, like depending, like for a Gaussian kernel, it would say points that are closer have a more influence on the position x than points that are further away. No? It's just for the Epanechnikov kernel that all points are equal, so as long as they are within that disk. Okay. If we can also talk later if there's something. Yeah. Mm-hmm. Okay. Okay. Let's have a conversation about cluster shapes. So a clustering depends on the distribution of the underlying data, obviously, probably, and the optimization objective of the clustering algorithm. We already touched the relation between the objective function of k-means with possible constraints on the Gaussian mixture model covariance matrices. You can also repeat this in a minute. So mean shift interacts in a somewhat unique way with the data, which at least theoretically might lead to a very particular clustering result. And now let's think about it, like what happens, or what type of results could we possibly create with this way of having these like mean shift iterations. Maybe before we start with this, let's recap k-means and the Gaussian mixture models really quickly. Yeah? So the k-means objective, can have a look at it really quickly. And so for k-means, what did we optimize there? What was the optimization criterion for k-means clustering? Sorry? Yeah, the within cluster distances for all the prototypes, yeah, within cluster distance. So this is something like a sum of squared distances of every point to its closest prototype or vector, mean vector, whatever. Yeah. So if we have a couple of points, this is the center, then can sum up these distances. This is then some barycenter or something, no? in these points. And if there's another center, no? Then this would attract the other points. Let's say, you can think about it like that. We have a boundary between them. So this is the k-means. Okay. What happens for the Gaussian mixture model? So more complicated. I mean, the fitting is more complicated with the expectation maximization thingy. But at the end of the day, what is optimized? Sorry? Yeah. It's essentially the likelihood. It's a likelihood, no? Yeah, or log likelihood. Yeah. Mm-hmm. So log likelihood of of observing this data given the means and the covariances, no? And the expectation maximization just did it in this like two-part iteration that we said, okay, like in one iteration we want to get the likelihood for the hidden variables, no? Like how likely is it that component I produced this data? This was the hidden variable Z. Yeah? And then in the second iteration, we said, okay, now let's optimize the means and covariances in order to maximize that likelihood. No? So again, we can have a couple of points here. We can have a mean here as well. We can have a covariance matrix, which is just like as some isoline of some, let's say, something like the equivalent of a standard deviation just in multiple dimensions, no? To indicate the overall shape of the covariance matrix. We can make a couple of constraints here on the covariance matrix, by the way. So common representations or common constraints. Let's write common constraints on the covariance matrix. What could be simplifications That makes sense. Okay, we can start with no simplifications. Yeah, we can just say, okay, like we want to have a full covariance matrices, so no constraints. These are full covariance matrices, sigma 1, sigma 2, if we have 2 of these clusters, for example. Yeah, they need to be positive definite, certainly, and so on. But yeah, but other than that, these are just arbitrary matrices. Oftentimes, though, I mean, this means how many parameters do we need to estimate? Depends on the dimensionality of the data. No? And then we have these matrices full with entries, like something in the order of d squared times k entries that need to be estimated. So people say sometimes this is a bit too much estimation for my taste. No? Let's simplify things a little bit. What would be simplifications that reduce the number of parameters that also may make sense? I mean, maybe it's not too much of a restriction. What could you do? Did we talk about this, Sylvie? Yeah? A covariance matrix of? Identity matrix, yeah. That's a possibility. No? So actually there are two possibilities. Yeah? So we can say we have one parameter per dimension, and we have one parameter per matrix. So if you say we take the identity matrix, that would be the third possibility. So we say sigma 1 is an identity matrix of a certain size multiplied by a single scalar as sigma 1, so something like this. No? And sigma 2 accordingly. So then for the covariances, we only need to estimate 2 factors, right? One parameter per dimension is like a compromise between these two. So we could say, sorry, I need to squeeze this in here. We could say, sigma 1 is a diagonal matrix, but on that diagonal, every entry is a separate parameter that we estimate. So this would be something like sigma 1, 1, sigma 1, 2, until sigma 1, n, right? Okay. So I think these are the 3 possible matrix variants that one might want to estimate for a GMM fitting. If we say we draw these covariances like this, how would the pictures for these 3 variants differ? So what would such a covariance matrix look like? What would such a covariance matrix look like? Yeah. Yes, the third one is just a sphere, d-dimensional sphere. Yeah. Mm-hmm. Mm-hmm. Yeah, exactly. Yeah. So this is like a d-dimensional sphere. Whoa, I screwed it up. Okay, but anyways, like a very round sphere. Yeah. This here is like an axis aligned ellipse. So something like this or that are possibilities. Of course, it doesn't exclude also to create a sphere. And this one is something like a rotated ellipse, no? Because we can have interactions now between different dimensions. So it can also be something like this, no? Yeah, exactly. How harmful are these differences? Well, it depends, no? But often enough, these spheres are not so bad already, no? And if you look at how little parameters you need for them, then there's really there's good reason. There may be good reason to use a very simple model, no? Now, if we compare this to the k-means with the sum of squared distances, the k-means effectively corresponds also to a criterion like these spheres, because it doesn't distinguish between the directions. So in all directions, it's equally good or bad or so, no? Whereas with these other shapes, you could have a preference for a certain direction, and there's even like an artifact for this is in the slides, and I forgot to last time to bring this to your attention. Let me do this really quickly now, because someone after the lecture talked to me, and then I realized, like, oops, this is something I wanted to show to you. Yeah. Look at this result. Sorry. So here, this green point here is really weird, no? But it's not a mistake. So this green point is actually really close to the red, to this center here, but it's not orange, it's green. And the reason for this is that we don't have a spherical shape here, no? But instead, the covariance of the green, I didn't write it down, unfortunately, but anyways, the covariance of the green cluster must be something elongated like this, no? And then there's still reasonably high likelihood that this data point has been created by the green cluster as opposed to the orange cluster. No? Okay. So this is a possibility for the GMM fitting. Now let's talk about the mean shift criterion, if you're fine with this, yeah? So let's go to mean shift. Like here we have this situation that we locally look at these like circular spheres and then always calculate the average of the points within the sphere and move towards some mode in that density. So what does that mean or imply or so for possible cluster shapes? I mean, it's not necessarily spherical or anything, no? Yeah, essentially, like anything can happen. No? I mean, it only depends on your little domain that you're looking at. No? So the mean shift cluster shapes they are only constrained by the distribution of data along the gradient ascent path. So we could create very peculiar things as long as it leads to a gradient ascent. No? Like, for example, we could craft something like this. So let's imagine it gets denser, 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 denser. Such that if we start here, we move all the way here in the circle, and other points here on that trajectory would take the same path. So they would all be put in one cluster. And then you could say, and now I'm sort of doing something weird. I mean, it's a bit synthetic, everything here. No? It's not this is not real data. But just as a mental exercise, no? We could now build a second trajectory that gets denser, 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 such that this cluster here moves like inside of the other cluster. No? And they, as long as their area of support, as long as they don't touch each other, no? I mean, like everything is possible. No? It's not really. There's not any contradiction to that. Okay, and I think this is just a property of having such a very localized criterion for evaluation, no? And this sort of decentralized process, like every point should just move to a local maximum, no? Then very different things can happen here. No? Well, I mean, real data is not that complicated. No? Real data typically lumps together. No? And this is also why the heuristic with, let's use these identity matrices with a single scalar, they work reasonably well in practice. No? But this is because oftentimes data is lumped together like that. No? And then it doesn't really, like these local criterions, so they don't really make a difference there. No? But just from a mathematical point of view, of course, it's a different type of procedure. Okay. Okay. Can we continue? Now there's the question, what is a good K for K-means? No? How many clusters are there in the data? And as one example to establish an objective function, we had a look at the so-called gap statistics. No? And gap statistics says, okay, you need a reference distribution. Can apply k-means to it with a certain k, and then calculate the difference of the within cluster distance of that k clustering to a K-cluster clustering of your actual data. And you can keep doing that for increasing K until you realize there's you don't really get better, like this gap doesn't really get bigger anymore, no? And then you stop. So that's the idea of the gap statistic. But I think the idea is really nice, and I just want to make sure that we're all on the same page and kind of understood this. So let's just restate a couple of things. So first of all, let's start with a set of uniformly distributed data points. I make a bit of space here, wipe the board, and then we have more space to draw things. So in the meanwhile, think about these things. So what does a clustering of uniformly distributed data look like into K clusters? And then why is the within cluster distance of such uniformly distributed data an upper bound for the within cluster distances for all data distributions? And then let's talk about this gap selection criterion in a minute. Oops. What can we say about uniformly distributed data and the K-means clustering of that? Yeah, we could assume there's no structure in the data, meaning like there are points everywhere. So if we want to divide this into K equals 6 clusters, what might it look like, the result? Mm-hmm. 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 There are points everywhere. If we should now put this in 6 clusters, depending on where exactly the data is now located, maybe these are the resulting cluster centers. No? I don't know. Maybe like this. No? And then we can construct the cluster boundaries by looking at the lines between the centers. No? Something like this, 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 if it makes sense. Probably yes. Oops, no. Okay. Somehow like this, no? Like that or similar, yeah? Okay. So it means the space is more or less equally divided. No? Also, if we think about the within cluster distances, it's going to be some, let's say, average distance of the points in each of these clusters. No? So you can say it's like almost like a proxy here for the area of such a tile. No? And these tiles more or less equally cover the domain if we have enough data. No? So this all gets a big variance probably if we have only very few data points, no? Because then also a uniformly distributed sample can be a bit skewed, no? So all that we're saying is like the assumption implicitly is there are enough samples such that indeed this is fairly homogeneously covered, enough observations. Okay, but then the situation looks like this. The universe more or less is split into more or less equal parts. And the within cluster distances more or less reflect the areas of the individual tiles, no? Connecting like all the points to these prototypes. Okay. So now let's just make sure that we have a bit of an intuition, like a working intuition without a formal proof or so, but why the within cluster distance of such uniformly distributed data. So let's say we have n points, and we have different choices how to distribute the data. Yeah? So how are they distributed? And then that we understand that from all possibilities to distribute these data points, if they are uniformly distributed, then it implies that the within cluster distances, statistically speaking, is maximal. Yeah? This, by the way, is a variational problem. We're going to talk about variational problems very soon. But how could one argue that such a uniform distribution maximizes the within cluster distance? If it were our task to convince someone that this is truly the case, how could we develop such an argument? And you don't need to put up a full proof or anything, no? But I just want to tune you in on this type of like thinking. No? What kind of argument could we invent? Mm-hmm.
In uniformly distributed data, there is no, so to say, structure. So the within cluster distance should be maximum.
One could think about an argument, no? To say, okay, let's make a 1D space, no? Just for clarity. So let's say this is our space. And this is the likelihood that we're seeing some data in that space somewhere. No? Okay. Now we say, yeah, let's do a uniform distribution to begin with. And we said, okay, like if we have enough observations and so on and so on and so on, then K clusters will split. So let's end our domain here. K clusters will split this space in approximately in equally sized regions. No? Within these regions, we calculate our within cluster distances. No? We come to this and that result. No? Okay. And now we can look at an alternative. Yeah? And this is like the variational spirit then. No? So what happens if we redistribute a little bit of that probability mass in that space? So then it's not a uniform distribution anymore. So let's redistribute somewhat. So redistribute some probability mass. So this means we have to take something away from some location and put it somewhere else. No? Okay. So we can, for example, say we make this a little bit lower, and then the rest remains unchanged. And whatever we saved here in this first quadrant, we can say it shall remain in that quadrant. And all that we're doing is that we're piling it up here. Yeah? So it's still in the same quadrant. We could also have put it somewhere else, but it's still there. So if we are splitting the space, probably the splitting will still be the same. No? But here in this quadrant, the within cluster distance just decreased. Because it turns out if I have my cluster center here, then I have a large number of points suddenly that is closer, and it's a squared distance, the within cluster distance. So closer brings a tangible benefit, yeah, because it's a nonlinear growth then of the cost. And the more remote locations, they just got fewer. No? So my within cluster distance got smaller. And a similar argument could be pulled if you say, okay, I'm taking this and I'm moving it to some other location. Yeah? But it's a bit more complicated. But this is the variational way of thinking about functions. So we want to maximize, or in that case, we have the property that we are maximizing one metric, the within cluster distance, by playing with, let's say, some function that goes into it. And this is our distribution function, like our probability distribution function, which in the case that we have a uniform distribution happens to maximize the within cluster distance. No? So, okay. Okay, so this is not really a proof or so, but this is the way how to think about this type of problem. Yeah? Okay. Yeah, so the uniformly distributed data is, let's say, one extreme, and any change in a uniform distribution reduces the within cluster distance. So, and in that case, like all other distributions are cheaper with respect to the within cluster distance than this uniform distribution. No? And this is, and we're seeing this, you probably recall this from the video. No? We're seeing this in this plot. So for each of these cases, the clustering of these of these uniformly distributed data points has a higher within cluster distance, and this is log scale, by the way, so in the actual numbers are way higher, but even in logarithmic scale, the within cluster distances of these uniformly distributed data is always larger than what we see in orange here, the within cluster distances of our little like distribution that we're trying to fit the data to. Yeah? Okay. All right. Yeah, so and this is what is then used for the gap criterion. Sorry, let me briefly go back to the slides. No? If we look at the difference between this uniform clustering and the clustering on our actual data, then we can say what the gap criteria, what the gap statistics does is it keeps increasing the number of clusters until it adds a cluster that doesn't really bring an additional benefit with respect to finding even more structure in the data. Yeah? So it still brings a net benefit to have 4 clusters rather than having just 2 or 1 or so. But compared to 3 clusters, the 4 is not such a big gain anymore. No? And 4 minus 1 standard deviation even. So this would be the reference point in order to avoid, let's say, bad luck from drawing some unlucky distributed points here. Yeah? Okay. So this is why we say, okay, after, like if we look at the fourth one is not as good as the third one. So then we say, okay, let's stick to 3 clusters, and this is where we stop. No? So this is the idea of the gap statistics. And it doesn't even look at what happens down the road here. Okay. Now, I don't know whether you had a look at this paper in Stud on the mean shift, but I essentially copied it also to the slides. If when checking the mean shift paper, they give a whole lot of reasons, like how could you choose the hyperparameters, how could you choose the bandwidth, so the kernel size of the mean shift algorithm. Yeah, and I was just summarizing this a little bit here in 3.1, the bandwidth selection. Yeah, they say, yeah, there are different ways how you can select the bandwidth. The first one is you could look for some best compromise between bias and variance of the estimator. But if you recall, bias and variance were something that we could calculate over the sets of all data sets that could be drawn from that distribution. So it's a rather theoretical argument, no? Because in practice we have exactly one data set. So this is the data that we have. And it's not that we have so and so many draws from some infinite pool of data. A second possibility is to say, well, let's choose a bandwidth for which if we change the size a little bit of the kernel, essentially for a large range here, value range, we get the same number of clusters. No? And you could say, okay, this is a typical heuristic, no? So typical ad hoc decision that you say, okay, if there's not a lot of change for that kernel size, then apparently maybe we locked into some structure. Yeah. And the third possibility is, yeah, maybe we can define some objective function like intra-cluster versus inter-cluster distances or so, which is, by the way, a bit in contradiction with the considerations on the, no, I wiped it away, but the mean-shift cluster shapes, no? which could be entangled, but okay. No? Or maybe just follow the downstream task, like what do you need that clustering for, and then decide based on that. So these are all more or less ad hoc ways of describing, of choosing the bandwidth. And for the Gaussian mixture models, we haven't carried it out because it will be subject of future lectures, but we went in the exact opposite direction. No? We said, yeah, okay, look, it's a fully probabilistic model, so not a problem. You want to choose hyperparameters, just declare them to be distributions, endow them with priors, no? And it's all part of the mathematical framework. So these are two very different ways of thinking about solving the problem. No? And yeah, I wanted to talk to you a little bit about what to do when, or what if we would need to give someone a more hands-on, a practical advice, what should we do? No? Any experiences? Any thoughts? Own projects? Anything? Not? Well, I think, okay, I was talking a bit badly about these, let's say, ad hoc selection methods that are listed in mean shift. But to be fair, I think in many practical scenarios, this is just what you do. No? You say yeah, okay, let's try a parameter like this, or let's try a parameter like this, that, and let's see how things go. No? Because usually this hyperparameter selection is just one problem that you need to solve among 500 other problems. So you just fix it somehow. And you do a couple of, a limited set of experiments in order to convince yourself that it's not totally stupid what you're doing. Yeah? And this is pretty much what is described, for example, in the second bullet point. No? And I'm not saying you should literally translate that strategy, but I think it's a very good depiction of what oftentimes, when it's about putting some solution together, what is very much advisable. No? To say, okay, I chose that parameter, it looks like a reasonable magnitude, and also if I wiggle around a bit, things do not change too much. No? It's a reasonable strategy. Or also something written under the third point, no? Depends a bit, or under the fourth point, no? To say, okay, the third point, if the result that I'm getting for some reason looks like a cluster, so looks like could also carry some mathematical meaning in the sense that I have a reasonably large intercluster distance, something like that, no? Or in the fourth point, I have something that works well in the application, where I plug this in, and it's totally fine, and you can move on to your 500 other problems that you need to solve. No? But of course, like for none of these solutions you get any like beauty prize or anything, no? Because it's really, so I just chose that number and it kind of worked type of approach. No? And here, like if you say, okay, I have a full model and so on, I'm expressing my distributions, suddenly you make this your primary problem. If you have 500 problems, that's okay, but they must wait a little bit, because now we're looking literally at a Bayesian framework of all of these distributions. Yeah? And from a practical point of view, choosing a good prior distribution for these means and these covariances that we are going to fit, and a good prior distribution here for our number of clusters is really tough unless you're working in a domain where, like by definition, you already have a good prior knowledge. Like for example, physics problems, no? You can use, they give you like wonderful priors for these distributions. No? You can just plug it in. But if you are in a less constrained environment, then oftentimes you have no clue what prior to choose. So if you want to, so then you have to make two choices. So either you say, I don't care, I just take one prior, but then you're not so much better as in the other scenario. Or you say, well, okay, I start to research into what is a good prior, but then it becomes very tedious. No? So, and this is why I'm saying, like, then your other 500 problems have to wait a little bit. But the benefit of this, of course, is that in itself, it's a very rich model. No? You have a distribution for everything. So by its definition, it's much more informative than just a point estimate. We touched a little bit upon this when I was touching this Bayesian linear regression one day here. No? So having a distribution is always more interesting than having a point estimate, but it comes at a hefty price, no? Because your distributions only make sense if your inputs make sense and your priors make sense. And this you have to make sure first. No? So I think it's good to know all of this, but at the end of the day, what you're using, this really depends on where you end up then in your professional life. No? Okay. Yeah, I think that was all that I wanted to say. Oh, sorry, I lost my question sheet. Here we are. Okay, any other things that you want to discuss? Then maybe let's call it a day for today. Thank you, and see you next week.